Good morning, everyone. This is M. Venkatesh, Assistant Professor in Electrical and Electronics Engineering, PVR Viswadaya Institute of Technology and Science, Kavali. Here, I am giving a lecture about electrical technology. This electrical technology is a subject for second BTech ECE students. So, what is electrical technology? Electrical technology basically deals about the electrical missions. So, what is a mission? Mission is nothing but a device which converts one form of energy into another form of energy. So, the electrical missions are classified into two types. One is DC missions. So, another one is AC missions. So, here the DC missions again classified by their generation and utilization of energy. So, that are DC generator and DC motor. Coming to AC missions, AC missions are again classified into transformers, induction motors, synchronous missions. So the synchronous missions again classified into synchronous generator and synchronous motor. So here the generator and motor are both are DC missions and AC missions. So there the generator can generate the electric power, the motor can consume the electric power. So let us go for electrical technology in the unit number 1, that is the DC generators. So the DC generators consists of introduction of the DC generator and principle of operation of the DC generator and constructional details of the DC machine, EMF equation of the DC generator and problems on EMF equation. So in this lecture, I can explain only first introduction and principle of operation of the DC generator. Coming to introduction, what is the DC mission? So DC mission is nothing but a device which converts one form of energy like electrical or mechanical energy into another form of energy like electrical or mechanical energy. So the DC missions can convert electrical energy into mechanical energy or mechanical energy into electrical energy. So that is vice versa. So a mission which converts mechanical energy into electrical energy, that is called a degenerator. A mission which converts electrical energy into mechanical energy is called a motor. So constructionally, the DC missions are both the same for the generators and motors. If we can provide any type of energy like electrical or mechanical which converts another form, that is like electrical or mechanical. So that's why suppose if you give the electrical energy to a DC machine, that give the output as mechanical energy. That's why that machine acts as a motor. Suppose if we can provide the mechanical energy to the DC machine, that machine gives the output as electrical energy. So at that time the DC machine gives the, it acts as a generator. So this is simply acts as either generator or motor. So that's why the DC missions are called dynamos. DC missions are called dynamos. So in these DC missions, we should know about the basic laws, that is a Faraday's laws and so Faraday's laws. So what is the Faraday's laws? So the Faraday states that the Faraday's first law and Faraday's second law. What is the Faraday's first law? Faraday's first law states that the conductor cuts the fluxes. Due to that cause, they induce the EMF. Conductor cuts the flux lines due to the EMF induced. So what is the Faraday's second law? So Faraday's second law states that the any form, so any electric induced EMF is directly proportional to the any induced EMF is directly proportional to the rate of change of flux. in the magnetic rate of change of flux. So these are the Faraday's first law and second law. What is first law here? The first law states, the Faraday's first law states that simply whenever a current carrying conductor cuts the magnetic flux, due to that induce the EMF. What is the Faraday's second law? So whenever the induced EMF is directly proportional to the rate of change of flux. Rate of change of flux. So here we are getting a term EMF. So the basically EMF is induced due to the cutting of the fluxes by conductor. Due to the cutting of fluxes by conductor. That's why the basic terms is to generate the EMF is flux, motion and conductor. So here what is the EMF? EMF is nothing but electromotive force. So EMF is nothing but electromotive force. So it is simply a force which drives the electric current in the circuits. The force which drives the electric current in the circuits, that is the electrical circuit, that is called a electromotive force. So this electromotive force can generate in the two types. One is statically induced EMF, another one is dynamically induced EMF. So what is the statically induced EMF? Means whenever a stationary conductor cuts by the moving flux. Moving flux. That means the motion of the flux cutting to the stationary conductor. So that's why they induce the induced EMF. That induced EMF is called statically induced EMF. Where we are getting the statically induced EMF here? In the transformers. In the transformers. Coming to second type of induced EMF is simply called as dynamically induced EMF. So this dynamically induced EMF is nothing but a motion of the conductor. Any moving, that is rotating conductor, cut the electric flux, cut the constant flux. So the rotating conductor cut the constant flux, they induce the EMF. That EMF is called dynamically induced EMF. Where we are getting the dynamically induced EMF? Which device will produce the dynamically induced EMF? Means simply generator. Generator is the induce the dynamically induced EMF. So that's why this dynamically induced EMF is the principle of operation of the DC generator. So that's why this dynamically induced EMF process is also called as Faraday's laws of electromagnetic induction. This is the working principle of DC generator. Faraday's laws of electromagnetic induction. This is the working principle of DC generator. So coming to in the EMFs, so we are getting the two types of either statically or dynamically induced EMF. So in the generators we are getting dynamically induced EMF. So in which direction we are getting the dynamically induced EMF? How to know? Means we can see the basic fundamental rules. So what are the fundamental rules? Means right hand thumb rule. That is the first one is right hand thumb rule. So here you can take any one of the conductor, that is a current carrying conductor. So that conductor can simply pick right hand, pick the right hand, simply like this. So pick this direction. You can handle the like this direction. So when you have picked the conductor in this direction, that in this style, the thumb is indicate the thumb direction. This thumb indicates the direction of the current. I is here, the current. So direction of the current, and remaining curved fingers indicates the flux direction. Curved fingers, flux direction. That means magnetic field direction. This is the right hand thumb rule. This is the right hand thumb rule. So another one more rule is there, that is simply Fleming's right hand rule to get the direction of EMF. This is the second rule. So Fleming's right hand rule. So in the Fleming's right hand rule states that you can take a right hand and the three fingers like this here. That means what? Here. So thumb, forefinger and middle finger. These three fingers placed in the perpendicular to each other. That means 90 degrees to each other. So that means 90 degrees to each and every finger. So at that time, the thumb indicates the motion of the conductor, and forefinger indicates the direction of the flux, that means magnetic field, and middle finger indicates the direction of induced EMF. That is the Fleming's right hand rule. So this Fleming's right hand rule is the principle of the DC generator. So by getting the induced EMF in the generator by using the Fleming's right hand rule directions in the so next one is Fleming's left hand rule. This is useful in the DC motors. This is useful in the DC motors. So, but here this is the basic rules to get the which direction we are getting the induced EMF. That's why I explained in the two rules here. So Fleming's left hand rule. So in the Fleming's left hand rule, similar to the Fleming's right hand rule, take the left hand and take the again three fingers, thumb, forefinger, and middle finger, and place each and 90 degrees to each to every finger. 90 degrees each and every finger. So here the thumb indicates the motion of the conductor, and then so middle finger indicates the direction of the current over induced EMF, and so forefinger indicates the direction of the field, like this type. So you can arrange like this type. That is so three fingers. So left hand, it's the left hand rule. So if you can take right hand, it is a right hand. So that is the Fleming's right hand rule. So here, so next we can see how to operate, how to get the induced EMF. So here it is a generator. So what is the working? What is the operation of a DC generator? How to induce the EMF? How we can get the induced EMF? In which way we are getting the induced EMF? What is the process is going on to induce the EMF in the generator? So let us see here. Here I am taking a simple loop generator. I am taking a simple loop generator. So in this loop generator, the induced EMF is directly proportional to the rate of change of flux. This is coming from the Faraday's second law. We know that the EMF induced in the directly proportional to the rate of change of flux. It is from the Faraday's second law. We know very well about this Faraday's second law. So here I am considering a simple loop generator. So in this loop generator, I am taking the two magnetic poles, that is a north pole and south pole. So different poles, that means north and south. So unlike poles, that means they have some attraction force. Due to that attraction force, always a magnet can produce the flux line, that is the lines of force from north pole to south pole. So when the flux passes from the north pole to south pole, these two are fixed poles, that is the north and south are fixed poles. So that's why they produce the flux lines of statically, that is a stationary flux, a constant flux passing from the north pole to south pole. So here I am placing a simple magnet, that is a coil, that is like this, a rotating coil. They have some motion, but initially I am placing a stationary coil. So that coil having the four corners A, B, C, D, like this. So in this coil I am placing the stationary flux. So at this let us take this coil can rotate clockwise. So then rotate clockwise direction. So at this stage I am taking the first case where the 0 degrees, at the 0 degrees, that means initially 0 position. So initially 0 degrees position. At that time, what is the flux? So initially there is no rotation of the conductor. So but there is a flux linkage is there, and here I am placing a conductor. But there is no flux cuts. There is no flux cut. That means there is no cuttage. So there is no cut the fluxes. That's why there is no induced EMF from according to Faraday's laws, first law. So that's why there is no EMF at the 0th position. Coming to, I am changing the direction. That means so 0 to 90 degrees. So when I am changing the direction, that is changing the position from, it is a clockwise rotational. So in the rotational way, so the coil rotates from 0 degrees to 90 degrees. So during the process, it is a rotating conductor cut the magnetic fluxes. So it is changing the position. So from 0 degrees to 90 degrees. Due to that case, what happened? The magnetic flux is a constant, but the coil is rotating conductor. So due to that, it cut the flux lines. So when it cut the flux lines, so they induce the EMF from the Faraday's laws of first law. So that's why they must having the EMF. Okay, so here it is a rotational conductor cut the EMF flux lines, stationary flux lines. That's why the induced EMF in the form of rotationally. That means dynamically induced EMF here. Okay, so coming to next position. So here again you can take another position. So that means here you can observe the coil. Here you can observe the coil. It can change the position. You can change the position from 180 degrees, 90 to 180 degrees. So when they change the coil, that coil gets again the previous position of A, previous position of A. That means 0 degrees position. So due to that 0 degrees of position, it is normally each perpendicular to the flux lines, but there is no movement. So it is changing the position and comes to the initial position. That's why they have some induced EMF that is a very minimum quantity. That is a very minimum quantity. So coming to next, we can change the direction of the coil from 180 degrees to 270 degrees. So that means the position number D. So due to that, the coil can go into the, so in the clockwise direction, and again it is changes from 180 degrees to 270 degrees. Due to that process, they cut the flux lines. They cut the flux lines. So similarly, they also induce the EMF in maximum quantity. And last two stage, that is a complete cycle from 270 to 360 degrees. From 270 to 360 degrees. That means again it comes to the A position. What happened here? Similarly, it comes as it is as a similar point position, that is a position. That means so there is no flux linkage. That's why the EMF is going to be 0. So this is the process of generate the induced EMF. So that means what you can observe here. So you can take a simple poles. So that is a north and south. Between the north and south, they have that flux lines. And here I am placing a simply a coil, that is a rotating coil. So due to that rotational coil, initially position A, there is no rotation. That's why there is no flux linkage. Coming to B, 0 to 90 degrees. That means the coil going to be rotates. So that's why there is a rotation of the conductor and stationary induced EMF. So stationary flux. So that's why what happened? So they cut the flux lines by rotating conductor. That means they induce the EMF. That's why here we are taking the maximum. Coming to C, again it is moving from the, so 180 to 90 to 180. So there is, it is coming to as the initial position, that is a position, like a similar constant initial position. That's why there are also some minimum amount of flux linkage. Coming to next D position, 180 to 270 degrees. So the coil cuts the flux lines. So due to that, what they induce the EMF. And coming to last, that is the 360 degrees. So we are getting the this is a very 0 induced EMF. Why means it's going to be at a initial position, that is a 0 degrees. So that's why, so the EMF is induced as a 0, maximum, minimum. That means what? It's a alternating nature. It is a alternating nature. So it is a DC generator. It is a DC generator. That means what? Which converts the mechanical energy into electrical energy in direct currents. That is a direct quantity, indirect quantity. So that means, so but here we are getting the alternating nature. So how to convert this alternating current into direct current means we can use the slip rings and brushes combination. So that means the slip rings or commutator and brushes combination you use in the DC generator. So this is what is the importance of slip rings and brushes combination means the slip rings and brushes are arranged, that is the commutator and brushes are arranged in the coil. So this coil may produce the alternating current, that is produce the alternating EMF. That alternating EMF induced in the armature that collects the commutator, So this commutator may converts, this is the commutator. So this commutator converts the alternating EMF So the commutator converts the alternating EMF into direct quantity. Alternating into direct quantity. So that direct quantity collects the brushes from the commutator. So the brushes collect the direct current from the commutator. So this is the process. So finally we are getting the induced EMF. Okay, so this alternating induced EMF. So actually the alternating induced EMF induced here, this alternating induced EMF collects uh, from the armature to commutator. So that commutator is nothing but slip rings. So the commutator converts the alternating quantity into direct quantity. Alternating quantity into direct quantity, and brushes can collect the currents from the commutator. So these brushes made up of carbon. It's a very soft material. Okay, so this is a structure of simply arrangement of slip rings and carbon brush. So you can see here these two are slip rings arranged to the coil. So that is a coil, that is the armature rotating conductors, and brushes are connected here. So that is connected to the contact to the commutator. So that's why. So initially, commutator collects the alternating quantity, and brushes collect the direct current from the commutator. Okay, so this is the commutator, and this is the working of DC generator and induce the EMF, dynamically induced EMF. Okay, thank you. And next class we will discuss, next video we will discuss what is the constructional details of these emissions, and what is the EMF equation, what are the problems coming at the EMF equation. Okay, so thank you. Thank you for